Okay, so the lesson today is on the area between two graphs. And I've broken this into two videos. The first one is going to find the area between the graphs of two functions by partitioning the x-axis. And the next video will find the area between the graphs of two functions by partitioning the y-axis. So let's take a look at this. So here we have two functions, all right, and to find this area, and this is the area we're looking for, right in here. To find this area, there's two considerations. We need to know which function's on top, which function's below. We also need to make sure that they are continuous over this interval, and this top function must be on top during the entire interval. Okay, so let's see what this looks like. So here, we're just to define the area. We're going to take the integral over that interval. Okay, so we're going to take the first function minus the second function. All right, let's see an example of this. So here we want to find the area between the enclosed graphs, and here we have one function, f of x equals e to the x, and g of x, which is the square root of x. And they're actually giving us the boundary lines when x is 0 and when x is 1. And we can see that area right in here. So how do we find that area? Okay, so we're just looking at the interval, or the integral, from 0 to 1 of e to the x minus, and I'll just say x to the 1/2. Because that's going to be easier finding antiderivative there. All right, so to do this, let's do this individually. So this area would also be, if I took the integral of the first function minus the integral of the second function. Okay, now let's find the antiderivatives of these. So this would be the same as evaluating e to the x from 0 to 1 minus evaluating 2/3 x to the 3/2 from 0 to 1. All right, so let's evaluate these. So here we would get e to the x, and then here we get, that's e to the 1, e to the first, minus e to the 0. And then here, let's do this. Let's pull out this constant here. And then we would get, when we plug in 1, we'd get 1. When we plug in 0, we get 0. So when I evaluate this, I get actually e minus 1, and here I just get minus 2/3. And simplifying all that, we got e minus 5/3. And remember, this is going to be in square units because we're talking about area here. I don't know what those units are, but in this case we're talking about area, so it must be in square units. Okay, hopefully that makes some sense. Let's try with another example. So here we have the two functions, 10x minus x squared, and the linear function 3x minus 8. And you can see in the picture here that the 10x minus x squared is actually on top, all right? And the linear function is below. So we're trying to find this area in here. But what we need to find is these two intersection points. So let's do that. Let's find, so what we really want to know is when 10x minus x squared is equal to 3x minus 8. So let's simplify this. So I can simplify this to x squared minus 7x minus 8 equals 0. I could factor this, and I would get x plus 1 times x minus 8 equals 0. And here we see at x equals negative 1 and x equals 8. So those are my intersection points. Okay? So what we're going to try to find is to find the area. We're going to use the interval from 0 and from negative 1 to 8 of 10x minus x squared minus 3x minus 8. This here. Okay, so let's simplify this a little bit here. You can rewrite this as negative 1 to 8, and we would get negative x squared plus 7x plus 8 dx. And now we can just take the antiderivative here of each of these. So I would get negative x cubed over 3 plus 7x squared over 2 plus 8x. And we want to evaluate that between negative 1 and 8. Okay, so let's do that. And when I plug 8 in, I'm going to get negative 512 over 3 plus 224 plus 64. Right, and then when I plug in negative 1, I'm going to get 1/3 plus 7/2 minus 8. And simplifying here, I would get 243 over 2, or 121.5 square units. Okay, hopefully that makes some sense. All right, let's go to the next example. All right, so here we want to find the area of a region enclosed by the graphs y equals the sine of x and y equals the cosine of x. And we want to use the y-axis and their first point of intersection. So when we look at this graph, we can see we want to find this area here. So we see the cosine function is above, and the sine function is below. So we want to find this intersection point. And I know you see it right there, but let's see how we can find this. So I want to know when the sine of x is equal to the cosine of x. I know many of you already know this, but let's try this. What if I divided each side by the cosine of x? Well, what I did. So here, I would get the tangent of x. And here I would get 1. So I want to know What is the inverse tangent of 1? And certainly we would get pi over 4. Remember, we're only talking in the first quadrant here, because they did say first quadrant. So I know what happens other places, but we're just considering the first quadrant here. All right, so now we know our interval. So we want to find the area, okay, and from 0 to pi over 4, and remember the cosine was on top, let's take the antiderivative of this, so we got the sine of x, because the antiderivative of cosine of x is the sine of x, and then plus the cosine of x. So remember, the antiderivative of sine of x is negative cosine, so negative cosine minus a minus is going to be plus. And we want to evaluate this at 0 and pi over 4. So let's plug those in. So I would get, when I plug in pi over 4, I would get the square root of 2 over 2. And then when I plug in pi over 4 there, I would get square root of 2 over 2. And then minus, when I plug in when I plug in 0, I get 0. And when I plug in 0 to cosine, I get 1. Okay, and now when we get here, we're going to actually get a square root of 2 minus 1. And remember, this is in square units. Hopefully that helps.